So let's start the webinar for today. The topic is accelerating semiconductor processes control with advanced 3D optical metrology. I'm Samuel Lesko. I'm leading the team of application developments based in San Jose, California. And today I will discuss how optical 3D profilers can help monitoring semiconductor processes. So right now everyone is on mute to ensure that we have a quiet background. If you have any questions along this webinar, please use the chat box where you can enter your questions. We will answer those questions at the end of webinars, and if not enough time is allowed, we will answer to you directly by email. The webinar will be recorded and will be available offline, such as you can rewind it as well as forward it to colleagues if there is any extra further interest. So please do share if you find out the content suitable for others. So I'm Samuel Lesko. I'm leading the team of application development for nanosurfaces division. Our core competencies of that specific division from this large instrumentation company of Bruker concern actually surfaces. So we can measure surfaces with stylus and optical profilers, both white light interferometer based and focus variations principle with Bruker Electrona. But also we can further probe surfaces with atomic force microscopy, both in topography and further electrical and mechanical properties down to the nanoscales. We can also use the same atomic force microscopy principle but apply for nanoscale infrared spectroscopy with nano IR principle. Finally, we also, let's say, interact in a mechanical way with surfaces using tribology and mechanical tester, as well as nanoannotations or fluorescence microscopy. So today, the focus is really on non-contact interferometric profilers used to measure topography over different kind of applications we see in the semiconductors. So the main aim is to go through different topics from the front end all the way to the back end, such as we can use the result from interferometer profilers to better control the processes into semiconductor manufacturing. So we'll go through from bare wafer roughness, CMP monitoring, die flatness, as well as all the back end interconnect and packaging, such as redistribution layers, boundary source, BGA or overlay discussions. So here at Bruker, we have notably different profilers. Today, we will really put emphasis on to the non-contact interferometric profilers. So this profilers, by essence, in a principle, works in a very simple way. This is just a standard optical microscope in which we have added a special translator in a vertical axis to scan objectives, together with a digital camera to further post-process intensity images. The main difference is relies on using interferometric objective, which split the optical path into two arms. The first arm reflects to a reference internal mirrors, while the second arm reflects from the sample surface. And by recombining both arms into the camera, we create fringes or moire patterns with black and white level of intensity. So if we use a broad white illuminations like strong high brightness LEDs, if we look to a surface of ball bearing, we see a nice concentric cycles, which is pretty limited because of the low coherence of the light. So here we spot out exactly where the focus plane is, around plus minus 1 microns here on those rings. Instead, if we use monochromatic illumination, in our case green light, we spread out the moire all across the bead and create a nice moire all the way to the surface. So from those illuminations, we get two core modes. The first one consists on a motor vertical scanning while recording intensity at the different Z level automatically, and rebuilding the topography by checking out the focus plane. So in that case, the fringes with white illuminations only helps to find out where the focal plane is, irrespectively from the objective. And you see that we have quite a large vertical scanning all the way through the surface. This is called vertical scanning interferometry. Whenever we use monochromatic illumination with green, we speak about phase shifting. So in that case, we use a dedicated piezo scanning with a few, like less than 100 nanometer shift, while recording the change of intensity for every point. So from intensity change with respect to the piezo motions, we back calculate what we call the phase image, and the phase image actually is proportional to the height difference by multiplying with the average wavelengths of the green light. So two modes that help us to describe either, let's say, rough sudden step all the way to very smooth surfaces. So as a user, what can you expect from an interferometric white light interferometer profilers? Beside being non-contact and only interacting with sample with light, we definitely have a unique characteristic with non-contact interferometry profilers, which is a vertical resolutions independent from objectives. This is very important because this is all along the whole optical profiler type of microscope. This is the sole technique which allows a vertical resolution dependent from the chosen objective. So we can use either 1x objectives all the way to 115 objective. We will always get the same vertical resolution. Ultimately, vertical resolution depends on the mode you are using. The vertical scanning is around 3 nanometers, while the phase shifting goes around 10 picometers, so 0.01 nanometers. What is interesting is we still have the ability to use super long working distance objectives with, let's say, properly collimated light. We will still get and achieve such a very high vertical resolution, which will have practical impact. The second one is, across all optical profilers, there are a lot of discussions about what kind of ultimate resolution achieve. Here, we are not speaking about resolution, we are speaking about true vertical metrology below nanometers. So what you will see on the coming slide is a true example with real measurements of step below nanometers. And that's unique all over the optical profiler's words. So it's due to the performances of using interferometry simply. The third core attribute from white line interferometry profilers is simply its robustness. It applies on shiny and matte surfaces. You can phase to metal, or you can phase to oxide. Even in some cases, some transparent layer will be properly captured, as we'll see. So it makes it very robust all over different kind of application. There's also another element is this fringe acts like a barcode reader, so it's a very strong signals to noise ratios. And if there is no such fringe, there will be no data. For instance, the stylus profiler tend to smooth out the edges. In that case of interferometry profilers, we won't. We will see top and bottom and nothing on a vertical 90-degree slope, which help to have a very fiddle descriptions of the surface. And the last one is this technique allows some microns lateral resolutions, and it's limited by objective. The reason is the calculation of the height is very pixel independent. So each pixel is independent processing to collect z height, which help us to really push the limit of what we can achieve with optical profilers, and even beyond in some cases. That's not the case for instance, like a focus variation technique where you bundle multiple pixel. Is not the case of optical pen raster technique where you average out around the spot of light. So now I'd like to illustrate really how this attribute can help a user, especially in semiconductor environment. There's a few examples. The first one is we can use long working distance objective with a properly collimated light, such as we can measure high aspect ratio vias, like true silicon vias, and still get signals at the end. So aspect ratio of 1/10, 1/20, or up to 1/25, 1/30 could be described that way, while retaining the proper nanometer vertical resolution we have with vertical scanning. The other point is we can measure very low roughness, and by measuring means, for instance, on this case of silicon carbide mirror, we nicely see the grains and tiny scratches with a mean roughness around 0.07 nanometers. And if we put some kind of range for repeatability, we will easily be plus minus 0.01 or below. So you have a reliable way to measure a sub-nanometer roughness and put metrology or SPC control behind it. Also, as I was mentioning, this technique is very robust. And this is a great example where on this solar panel you have the silver lines that collects electron generated by the polysilicon, and in that case we can easily measure both silver line and polysilicon surfaces, while we have a very strong difference of reflectivity. And here it was measured in one single measurement. There is no trick of using HDR algorithm, and you still get data around. So it's pretty flexible technique, scoping with a high range of reflectivity. And last but not the least, an example of ultimate lateral resolution we can expect with that technique. So while we're using white light, we can still break in some condition the standard criteria of diffraction limit. So in that case, you see an example of photonic waveguide or crystals with hexagonal patterns of pillars of silicon oxide inside silicon, and this pillar gets 100 nanometers, 190 nanometers diameter spaced by less than a micron, and you nicely see that everyone is nicely insulated, reaching the true lateral resolutions of 200 nanometers. So you can apply this technique to really reach out amazing lateral resolution and distinguish line space by 200 nanometers, for instance. So to finish with all those attributes, white light interferometry technique position very well versus other profiling technique. So if we plot out the vertical resolutions on the y-axis and lateral resolution in x-axis toward logarithmic scales, we can plot out the space where atomic force microscopy operates, as much as white light, SEM, scanning electron microscope, and stylus profilers. So what we see is SEM, in essence, is great for a certain space, but only allows top view 2D type. So it's all about CD-SEM. FM is mainly in use for super submicrons lateral resolutions together with angstrom vertical resolution. This addresses, and this is the sole technique, gaining 3D surfaces in that space. But for all the rest, coming from slightly submicrons to tens of millimeters, or from angstrom till a millimeter range, white line interferometry will play a role. And that's the reason why it covers a wide range of measurements into semiconductor processes, and it's very helpful to and complementary to the rest of the system. So now we will move on to the real solutions white line interferometry can bring. And first of all, we'll start with the front end processes. Usually for front end, the white line interferometry has a few application spaces. The reason is we have a limitation on lateral resolution. But in the meantime, we have ability to scope with large field of view, which make it very interesting for entry control regarding bare wafers. So what you see here is actually a series of stitch image to cover a full 10 millimeter by 8 millimeters. And the reason we stitch that kind of size is it's a typical size of dies. So the idea of this entry control for the silicon wafers is to define not only the roughness, so here you have a global roughness of 0.8 nanometers, which could be acceptable, but also you can automatically extract any defects. So here we have extracted the pits, so the small cavity you can find over there, and we have plotted the maximum depth in nanometers and ranked them from the deepest to the shallower one. And then we can estimate as well the extension in X and Y, so along this horizontal, vertical axis, such as we can define the aspect ratio and see whether it's a scratch or whether it's a more round pit. But the most interesting is here in 14 minutes we cover the full range, and we are still in positions to describe a defect as small as 1.4 microns. And later on in the process we can estimate and see whether this defect impacts the patterning and the photolithography processes or not. But the overall concept here is be able to quickly measure roughness. Usually a single image will take as short as a few seconds to be measured, or you can cover larger area and hunt for some defect and sample out the wafer that way. The next application is really one of the hottest and key application enabled by a white line interferometry technique. It is to deal with the chemical mechanical planarization. So CMP exists in semiconductor processes since the start. The idea is to make sure that at some point you make everything flat, even so you have a very heterogeneous structure. So here you have an example where you have dishing, erosion, which is unwanted, and you want to control that. So usually we use atomic force microscopy to do that, because it requires high lateral resolution, especially with the coming node below 10 nanometers and all the deep XUV lithography. However, what is interesting is a larger scale with a full die topography. And the reason being that whenever you go for memory control like NAND, you will add multi-layers over multi-layers. And if you don't control CMP very well, you start to create some erosions and dishing, unwanted ones, which will impact the thickness of oxide or metals and reduce the performances of the device. So it's very important to check out layer to layer how flat and smooth the surface is to a level of the full die actually. The other point is what we see, especially in imaging solutions, they are more and more hybrid or wafer bonding. Wafer bonding, especially in imaging, is made in a way that one wafer is processed to have the pixel connections, and the other wafers is made to have the active pixel. And by splitting the pulse wafer, we avoid metallic contaminations to the pixel side and make the pixel more efficient. However, you will have a molecular adhesion bonding between two wafers. In that respect, you will need this die-to-die flatness, such as adhesion can occur, and be reliable. So in that case, there's a need to stitch the full die and assess how flat it is. The last application concerned really the 3D and the advanced packaging into integrated circuit. So in that case, especially for mobile phone, you get a more and more complex stacking with a high density interconnect, shorter interconnect in terms of height. So all that works if you assume that the die is flat. Otherwise, you will have electrical connection issues, and one single issue will simply kill the full operations of the circuit. So it's the cost of non-quality here is absolutely high, as much as here it is with hybrid bonding, where you sacrifice two wafers being at the end of the process. So white light interferometry providers simply helps to measure the full die with enough vertical and lateral resolutions. So what you see here is a digital zoom in of the golden die thanks to the CLAT. And what we see here in blue is a certain dishing, and in red some protrusions. And we also notice there is a grid pattern which corresponds to the Damascene structure, which helps to fill in the region with fewer density of devices and making sure that the CMP process gets a more regular erosion. But as you can see, especially along this line, you have on the red protrusion for the same pad, and this pad goes all the way to getting a dishing, which is not wanted. So here locally you have a higher erosion of the wafer due to the CMP, which is not what is wanted. So in that case, having the full die stitch helps to define where the hot spots are and optimize the CMP process very well. A full die stitching with this lateral resolutions around a few couple of 2-3 micron only lasts for 20 minutes or less for 25 by 30 millimeter die size. So it's a pretty achievable and doable to check for improvement of CMP or fine-tuning on it. Of course, once you have this data, you want this data to be highly reproducible and to a level of nanometers, simply because whenever you see this dishing, which is usually in a range of a couple of nanometers, you don't want to repeat the measure and see this dishing becoming a protrusion, because in that case it is very conflicting on how you could improve a CMP process. So in that case, the whole trick to enable this application is how reliable, robust the stitch is, and the quality of the single image is as well. So in that case, to prove that, courtesy to the CALAT, the same golden die has been stitched post CMP, so it's the same die all over the year, and all the height distribution has been plotted. So vertically, you have the height level. Horizontally, you have the number of points which have this height level, and everything is plotted into the logarithmic scale on horizontal C to see and better understand what's going on that regions and here, because here is like protrusions region, here is really dishing region, so you really want those regions, even so almost close to the noise, to be very reliable. And you can see that over a year the dispersions is no more than plus minus 1 nanometer, which is required. So this die flatness application is really critical for the quality of the product. However, it stresses and pushing the boundaries of the technology over there. So having a 1-year reproducibility at 1 nanometer level means that you are spreading tens of atoms over regions of 25 by 30 square millimeter. So you can imagine the scale ratio is just amazing. So now I was finished with this last example for front end. So I was discussing really the defect on bare wafers. On that bare wafers, the defect are so small on the height that you can't really detect them by the standard defect inspection system, like the Candela system, not to mention them. The same thing happened on all the way around. So when on the processes you start to grow thick AP layers, especially for high power electronics, one of the issues you face is there is inherently some defects that propagates, and those defects become bigger and bigger as the growth of AP layers goes upward. So in that case, what's happened is this defect can protrude out from the wafer in a way that it will start to be hazardous for the next step, which is the photolithography. So in that case, you may damage the photolithography system while having this defect. And of course, you don't want to grow further those AP layers if they start to be already bad, otherwise you will lose a 1-week production slot. So in that case, it becomes very important to map out the defects on the wafers. But in that case, the Candela system will spot out the defect, but will not tell more information above a few microns or 0.2 microns. So there is a lack of information, and this is where white line interferometry with like 2.5x objective or 5x objective can quickly map out a 4-inch wafers and define the height of this defect. So what you see here is the label of height whenever there's a defect. So here you see 23 microns height, and on the green you see 1 micron. So in that case, there is a fully automated measurement that will last for a couple of hours and define the location and the height of every defect. So here you see that on the border you have defect, which is not that important. However, you start to have challenging defects over this middle region, which is critical, and this wafer needs certainly to be scrapped down to avoid destructions or damage on the photolithography system. So again, here white line interferometry for front end can really help to fine tune and make sure that there is no critical defects by proper quantifications. So now I said the solution for front end are limited to the point that the white line interferometry really gets some limitation for lateral resolutions around zero point 0.2 microns, which will be changing then to see the structure, and that's the reason why atomic force microscopy is in use. However, for back end, this is exactly the core competencies of white line interferometry technique because of the advance in 3D packaging. By integrating and making more miniature all the integrated circuit, there is a need of 2.5D 3D stacking technologies or wafer level packaging to process in a quicker way and assembly all the chip together or the fan out. So you get an example here of very dense bump array interconnect TSVs, and all that requires stringent metrology, because if there is one missing copper pillar or bumps, one electrical connection will miss, and the overall chipset is in danger of non-operations. So, and for to grow and get this TSV, grow the bump, you have several steps in the processes where you have to control the height, the diameter, the depth in a more systematic way at different steps of the process. And this is where white line interferometer can help. And it does help because there's a combinations of really four main parameters, which are hardware, analysis, automation, and skill. And by combining all of that, you end up with a solutions which help you to automatically, quickly get and spot out defects or deviation into processes. But for that, you need to develop dedicated hardware where you have a single vertical axis calibrations. Because we are based on one single mode, we have added extra interferometer, laser interferometer, to make it self-calibrated, such as it is reproducible on the machine, and it's also helps the tool-to-tool matching. You have to develop as well dedicated analysis, such as the measurements is quickly post-processed and the proper information is extracted in a correct way. And for that, you need to inbuild flexibility, because in terms of 3D stacking, really the pattern, the spacing, the shape will vary quite a lot from one product lot to another one. Last but not the least, the system need to be fully automated. So we are providing all the solution from wafer handlers base, for instance, having Cognex algorithm to really skew the wafers, or even centering the pattern, as we'll see. And last but not the least, you have to deal with certain number of skills, such as the best known method for analysis strategies is perfectly in place, where you can match tools to tools and get the throughput. And for that, at Bruker Nanosurfaces division, we are helped by our long experience in the data storages, having system in US, North Islands, in Penang, in Malaysia, combining all this tool into one single proper answer, accurate answers all the way through different regions. And once you have this, then you can start to really hit the road and enable process control. The first one is through silicon via. Usually you can find solutions with IR-based microscopy, but however, sometimes it lacks lateral resolution as well as vertical repeatability and reproducibility due to the fact of being based of IR. With white light interferometry technique, by using low numerical aperture objective, we can really collimate light all the way to the bottom and still get signals, which is weak, but due to the fact this is an interferogram patterns, we can see this black and white kind of barcode that they haven't reliably measure. So what you see here on the left is the cross sections of SCM of the same structure you see measured by white light interferometer profilers, and you see the third and second here and here are properly measured and seen with the depth of 43 microns and 5 microns width, which is 1/10 ratio almost. So we can get accurate measurements of trenches, notably if you're using bus processes for high power electronics, or to use TSV in order to have interconnects between dies. This capability to measure the true silicon via ranges to a wide scope. Here you have a summary graph where we plot depth and the width, the opening width, as well as a shape factor like trench or via, and we can go all the way from 100 microns depth with 20 microns opening all the way down to a microns with a depth of 25 microns. So this is an example on the right where you see the sections of measured by a regular 20x objectives, where we have a pitch of 1.5 microns, a width opening of 1.2 microns, and a depth of 34 microns. So what we see here is really a big aspect ratio of 1/20 just by standard objectives. So this is definitively an easy, non-destructive way of getting the real depth and monitoring etching depth in that way. And then we have all the redistributions layers that conveys the electrical power in between the chip. In that case of advanced packaging, this kind of RDL become very dense and having an aspect ratio of 2 microns width, 2 microns opening, and 2 microns depth as well. So in that case, we have to measure the real copper thickness to ensure that the electrical power will go through, and make sure that the surface resistance is low enough. In that case, we have developed a dedicated analysis where whatever the measurement we take with a series of lines like this, the system will find out the main orientation, the skew, the theta angle to align them pretty well, and then be able to measure each individual RDL fingers, measure the width fluctuation along this line, and get an average with average depth as well as much as an average fluctuations. We also measure in the same way as a single image acquisition. We will measure the roughness, top bottom. We have also ability to sections the RDL layers at the different height versus the full height. So get the top and bottom CD, for instance. For RDL, we have also to, in some occasion, to measure the polyimide thickness, and this is where the white light helps in terms of transparent layers. So what we see is the light will be reflected from the top of polyimides, like here, and also we will look for the light reflected from the silicon surface. So in that case, with one single measurement, the system can insulate a different focus point and get a map for copper thickness and for polyimide thickness, and get out those two information in a one single measurement. Same happen for the bump and recess. So whenever you start and grow the bump, there are multiple step, and each of the steps will require different analysis, which is the inherent need for flexibility. And here, with a single type of analysis, we can automatically spot out either holes or peaks or rounded shapes independently and extract for each of them the mean depth or mean height, having an idea of the diameter, and plot all that into a single database. So if there is any missing bumps, we will flag this by the number of bumps detected, or if there's any deviations over a certain width or height, we will also spot that out in absolute manner. So we can, along a die with very high density bumps, we can tell the absolute coordinates of that bump versus the origin of the die, and tell where maybe we can send some repair tool to flow back the ball, for instance. However, the structures are not that simple, and it's especially with advanced 3D packaging, RDL layers get very complex pattern, like some kind of serpentine structure, and this structure can actually be automatically captured with intensity image through the Cognex algorithm and be automatically recentered in a very reproducible way. In that case, even the serpentine can be properly masked in order to get exactly the same pattern of fingers, and we can use the previously explained analysis for traces and get the top, bottom, width city, space city, or height in one way. And this can be seen that irrespectively if you have a bit of offsets along the 300 millimeter wafer, the system would compensate for the offset and get it back. Further complexity in terms of pad height for instance, aluminium. It is quite frequent that sometimes the wafer itself can be rotated, or the pattern can be offsetted. So here you see an example of, let's say, the golden die, where you have the pattern and we have automatic analysis that will recognize its shape and insulate it and recenter it, and then measure the relative height difference between the pad and the rest of the silicon substrate, for instance. So here you see a value of 13.27 microns. So if you look to the same location, provide an offset and strong rotation here, the system will again recognize this pattern, rotate it, put it back to the center, and recalculate automatically the height in a great way. So it's really helped to get nanometer level reproducibility, but also helps tool-to-tool matching, where you may have a different theta orientation of the wafer due to the wafer handler, or slightly different offsets in that way. And the last application for back-end processes checking is really the via with the overlay. So we have developed an analytical tool called Vision Map that work together with our standard software. So such as the system will acquire one image, like the topography with 3D informations, and then the system will work out the CD analysis automatically, working out the radius, working out as well the offset between the bottom of the structure and the second layers. So the two layers offset can be worked out. And this toolkit is very flexible, so if it starts to be a square or a pill shape or some kind of a quarter of cycle, we can ensure that we tailor the recipe and extract informations in one single measurement, such as we aggregate into the same database 3D information such as depth, volume of the via, together with proper 2D CD applications like radius and X and Y offsets between the two layers. And this opened up a brand new structure of like automatic optical inspection through white line interferometry profilers, which is very interesting and threatening, making use of one single system instead of multiple. So as a conclusion, as you have seen, the 3D optical profilers based on white line interferometry can definitively support process control in semiconductor environments, both front end and back end. The main core reason that this technique is very robust, being independent from reflectivity and gaining sub-nanometer vertical resolution for all magnification. And it brings back fidelity of surfaces. It brings back as well the proper vertical metrology performances aligned with respect to the specification and requirement for the processes, together with especially large low magnifications gaining sub-nanometer vertical resolution. You will get throughput for defect detection. So it can be defect detections for bare wafers or for a dense array of bumps. It is also a question of throughput because you don't need to average or multiple the measurements. A single measurement will help to get that right away. And what you have seen so far is all the solutions is only contained with one single tool, with one single principle, one single optical path. It makes everything easier to control on the SPC level the system, because there is only one vertical calibration to check, only one principle of operation, such as you can make sure and assess the equipment in a quicker way while answering a wide range of application coming from roughness till CD measurements like automatic optical inspections. Thanks for your attention. If you wish to directly contact me, please feel free to use my email address, samuel.lesko@bruker.com. And now it is time for the questions. And in that respect, let's see what questions we have over there. So I have questions regarding on RDL layers, stating like what kind of lateral resolution we can expect. So in that level, we have already measured RDL layers of being 1 micron with 1 micron's opening and 1 micron's depth. The killing factor for lateral resolution is really aspect ratios, and aspect ratio goes quickly downward. So for sub-microns RDL layers, AFM will be the more indicated system. However, if you wish only to measure the top CD, we can still only use the optical contrast between those layers and measure through our vision map toolkit the width of this layer without being forced to measure the 3D. I have another question regarding, like you were mentioning, the transparency and a capability to look through transparent layers. What is the limit in terms of transparent layer thickness, and what kind of artifact can we expect? So Regarding transparency, we can easily measure transparent layers up to 100 nanometers thickness. So we will use interferometric signals to define and measure thickness of those films. Uh, that being said, below 100 nanometers, stylus profilers, AFM will be the reference technique. So there's the reason why we need some complementary system here to ensure that there is no more optical principle, because optical will always get some kind of spurious answer below that level. I have another question regarding CMP. So on a CMP layer, you have a lot of different refractive index and thin film like oxide. How do you scope with that for the measurements? So regarding the CMP, it's clear that we need to cover with very thin opaque film the whole wafer. It's, let's say, dexterosity weighs so far, and that will prevent us to get any issue regarding potential offsets in between refractive indexes or change of oxide thickness, such as we have reliable result. This result were cross-correlated with AFM measurement, so there is a tight correlation between what was measured with white line interferometry and AFM in such a conditions. The other possibility is to proceed with subtractions of a reference dye. So basically, in that case, it's fully non-destructive. We are not covering the wafer with any film. We're simply collecting the data on a good or golden reference dye, and we always subtract that dye versus the measurement to see the deviations versus the optimal dye. So now I've end up with the question. If you have any more question, feel free to reach us out at samuel.lesko@bruker.com. You can reach us as well through our website where we have extra elements and extra webinars recorded. Thank you for your attentions, and I look forward to get you on board for the next coming webinars. Thanks and goodbye.